Hi, are you sick and tired of fossil fuels? Do you want clean, reusable energy, but solar and wind just aren't cutting it enough? Is nuclear fission energy just scaring you too much because you think Chernobyl or 3 Mile Island will happen? Well, do I have the solution for you? Nuclear fusion. Now, I know what you may be thinking. Isn't nuclear fusion one of the greatest engineering challenges of our time? Yes, but I've developed a team with 4 undergrad students who've only had 3 years of education, and we have developed a nuclear fusion reactor to power energy for everyone across the world.
In case you guys didn't know, nuclear fusion is the fusing of atoms in which energy is released every time a reaction is made. Fusion reactions have been achieved in many different research labs, but were unable to be sustained for prolonged periods of time. To account for this problem, our design would function similarly to fuel injection systems to sustain the fusion reactions using pistons. There are two general types of fusion reactors designed. There's magnetic confinement fusion reactors and inertial confinement fusion reactors. Magnetic confinement fusion reactors use the magnetic field to compress the plasma into a donut-shaped chamber where the nuclear fusion takes place, while the inertial confinement reactor uses pulses from superpowered lasers to heat the surface of the pellet of fuel. Our design combines both of these confinement chambers to create a magnetized targeted fusion reactor. The magnetized targeted fusion reactor is similar to the magnetic confinement approach, where the fusion fuel is confined at a lower density by a magnetic field, while it is heated into a plasma, and similar to the inertial confinement approach, where the fusion is initiated by rapidly squeezing the target to greatly increase fuel density and temperature. This design makes it easier to build compared to the two main types of fusion reactor designs previously talked about. This design that we've made, though, will incorporate three main components: a plasma injector, which supplies the fuel, an array of pistons to compress the fuel, and a chamber of spinning liquid metal to hold the fuel and capture the energy. The fuel will consist of tritium and deuterium, the two hydrogen isotopes, which will be fused together. These are the most common sources used in nuclear fusion tests. The liquid metal would be composed of lead and lithium to capture the energy/heat from the fusion reaction. And the heat from the liquid metal would then be pumped into a heat exchanger to generate electricity through a turbine. This design would ideally be located by a body of water for cooling, similar to most power generation systems. The area would require good infrastructure for receiving materials for the fuel and liquid metal, and a main source of hydrogen/tritium and deuterium. For this, we've chosen Buffalo, New York. Buffalo, New York is situated by Lake Erie, and also the power generated from our reactor can easily power this big city. And this is our nuclear fusion reactor. As you can see here on the top, this is our first component, which is the plasma injector. It acts like a fuel pump would for an automobile, by being the source of fuel into the chamber. Being made out of a high entropy alloy, the plasma injector turns the fuel into plasma and encapsulates in a magnetic field. This sphere is our chamber for the reactor. It is about 3 meters in diameter with a tolerance of plus or minus 0.01 meters. The plasma injector is 0.33 meters within the chamber with a tolerance of plus or minus 0.03 meters. The chamber is surrounded by 84 pistons, all separated by 0.4 meters with a tolerance of plus or minus 0.02 meters. Both chamber and pistons are made of B861 titanium alloy for its heat-resistant properties. The properties of the magnetized targeted fusion reactor are as follows: being 4,600 kilograms per cubic meter, a mass of 33,000 kilograms, and the volume of 7.20 cubic meters. Now, as you see here, a piston array will be put around the chamber and is assembled with bolts. These bolts are made of high-strength nickel alloy, which is used because of its high resistant properties and high strength yield to prevent potential failures. As you can see here, we have our piston. And if the proper material and grade is not chosen for the bolts on the piston and for the design, potential cracks and failures will proceed to propagate. and then our design will fail. The size of the bolts are M20 by 100 millimeters with 0.08 meters from the top of the bolt and 0.06 meters for the bottom of the bolt, with a tolerance of plus or minus 0.002 meters. And this is a video of our piston firing. The piston will fire every second. And the calculations were done to show that the nuclear fusion reactor gives out 40 megawatts per second of energy. And this is our nuclear fusion reactor. We would like to acknowledge the 4 people who came on to help design this reactor, with me, Adam Mafi, Andreas Rowe, Jerel Houston, and Tristan. And we thank you for seeing our mechanical systems design project.